Welcome back to the second example on what is this? Subspaces, bases, subspaces and bases and linear combinations. I mentioned in the previous example that this video is gonna be one entire example that's gonna be fairly long, a little bit challenging, but once when you know how to do these, it should be relatively simple to do other types of questions or like similar to this one. But let's get started. I don't want to waste too much time. And so in this example, it gives us a matrix A, which is a 2 by 2 matrix consisting of 2, 1, negative 1, 4. And it wants us to show that there exists a set W of M2R consists of all 2 by 2 matrices in the real number domain that commute with A is a subspace of M2R. So that means that the set W is a subspace of all 2 by 2 matrices contained in the real domain, and that it also commutes with A. So that is the other condition that we need to look for. So let's get started with the first part that I already had underlined here. So first things first, we need to find a matrix that commutes with A. For those that don't remember, when it comes with matrices, and when I mean by commute, I mean like multiplying. The commutative property of multiplication exists. And so if you recall, like way back then when you guys were younger, when it comes to matrix multiplications, it's very difficult to find matrices that commute. We know that it's possible that if we have two matrices multiplied together, it is not the same, well in this case it will be A and B, it is not the same as B times A. And so that's the little bit of challenging part. So we need to find a matrix. In this case, we're going to call M, such that it is a 2 by 2 matrix. But we need to find one that's such that M times A is equal to A times M. So we're going to let M just be a 2 by 2 matrix containing A, B, C, and D. And now, because we have to check that MA is equal to AM, we can just substitute these two sides with M and A. So on the left side, we'll have A, B, C, D. That is a terrible bracket. A, B, C, D multiplied by 2, 1, negative 1, 4. And this is equal to 2, 1, negative 1, 4 multiplied by A, B, C, D. And so what we're going to do now is we're just going to multiply both sides into a 2 by 2 matrix, because we know that the columns of the first one is equal to the rows of the second one, because they're both 2 by 2. So our result will also be a 2 by 2. And so we're going to have 2A minus B, top left, top right would be, I don't remember how to do this. Oh yes, A plus 4B. And then this would be, for the bottom side, would be 2C minus D. And then C plus 4D. And then on the right side, it will be 2A plus C, and then 2B plus D, then negative A plus 4C, and negative B plus 4D. So we want to have, because both sides have to equal to each other, and because each like element is independent from the other elements, we can have a system of equations where we have this portion equal to each other, this portion equal to each other, this portion equal to each other, and then lastly this portion equal to each other. So I'm gonna put them all into one, or into 4 equations, and so we'll have 2a minus b is equal to 2a plus c, then 2c minus d is equal to 4c minus a. Then we have a plus 4b is equal to 2b plus d. Then lastly, c plus 4d is equal to 4d minus b. And then we're just going to move all the variables on the left side. And so what we have here, conveniently enough, the a's cancel out, or the 2 a's cancel out. And so what we have here will be negative b minus c is equal to 0. On the second equation, we'll have a minus 2c minus d is equal to 0. And then this third equation would be a minus plus 2b minus d is equal to 0. And then the last one, the d's cancel out, and you're left with c plus b is equal to 0. And so now if we want to solve this, we can just go into matrices, or put this all in an augmented matrix and solve for our a, b, c, and d. And so we have here, this would be a, b, c, and d. So it'll be 0, negative 1, negative 1, 0, 1, 0, negative 2, negative 1, 1, 2, 0, negative 1, 0, 1, 1, 0, and the augmented is all equal to 0. So right here, we have to put this in, row reduced echelon form. And here's what we can do. All right. So I don't even know I want to put this. Actually, okay. So when you put this in row reduced echelon form, I'll let you guys do it on your own, and I won't go through the steps since I don't want to waste too much time. When you put this in row reduced echelon form, you can check it yourself. This should give you 1, 0, 0, 0, 2, 1, 0, 0, and then 0, 1, 0, 0, and then lastly negative 1, 0, 0, 0. And so this is how it looks in row reduced echelon form. And as you can see here is we have our pivot here, then we have a free variable here and a free variable here. And so we are going to write this back in terms of like variables itself. So we'll have a is equal to 2b, not a is equal to 2b, it's a plus 2b minus d is equal to 0, and then we have b is equal to c, and then we have c is equal to c, and then d is equal to d, or c and d be any free variables. And so now we could substitute this in. This is plus c, this is supposed to be a 0. And so what we get here is that we have c is equal to negative b, and then here a is equal to 2b minus d, and since we know that, negative 2b plus d, and since we know that negative b is equal to c, A is just equal to 2C plus D. And so now we can substitute all of this back into our matrix M. So let me rewrite what matrix M was. A, B, C, D. And this is equal to, we're going to substitute our A and B. Since C and D are like any variables or basically a free variable, So A would be 2C plus D, and then C is C, and then we have negative C, and then we have D. And so now we have our matrix that commutes with A. So that means if we were to multiply this by A, so MA, we should be able to get the same result as A times M. So now what we have to do is check if this is a subset. And if you recall on checking what a subset, or how to tell if something is a subset, we have to check if the zero vectors involved, and if it's closed under addition, and then lastly if it's closed under multiplication, or scalar multiplication, my bad. So we're gonna go ahead and start with, let's see, which one do we want to do first? Addition? Yeah, addition. I think addition would be the move. We're gonna check if it's closed. I'm actually do this in the color. Closed under addition. So we're gonna let two matrices, gonna have 2C1 plus D1, and then we'll have C1, negative C1, and then D1. We're gonna add this to 2C2 plus D2, C2, negative C2, D2. And so when you add these two together, move this here. When you add these two together, we are going to get 2C1 plus 2C2 plus D1 plus D2. The bottom part will have C1 plus C2, and we'll have negative C1 minus C2, and then lastly we'll have D1 plus D2. And so and what we can do now is we can substitute these variables. Well, okay, actually here you can factor out a -1, so we have C1 there we go, C1 plus C2. And then here you can factor out a 2, C1 plus C2. And so now what we can do is we could substitute these some of these variables. So we're gonna let C1 plus C2 is equal to C bar, and D1 plus D2 is equal to D bar. And so when you substitute those in, you'll have 2C bar plus D bar. Bottom one would be C bar. The top right would be negative C, not a sub. There you go, negative C bar, and then D bar. And if you look at this is also the same thing as we had in the matrix M that we found, 2C plus D, and then the C, the negative C, and D. So yes, this is close under what is it? Under addition. This is close under addition. So now we have to check if it is closed under scalar multiplication. So under scalar multiplication. So we're gonna start. We're gonna just gonna use C1. So we're gonna have C1. Whoops, not C1. 2C1 plus D1, C1, then negative C1 and D1, and we're just gonna multiply it by some constant K. This is gonna be equal to K times 2C1 plus D1. Actually, I'm gonna just put it all in. 2KC1 plus KD1, KC1, negative KC1, and then KD1. And so now what we're gonna do is we're gonna substitute again like we did before. We're gonna let KC1 is equal to what's another, not K bar, let's do another K hat, or not K hat, C hat, and KD1 equal to D hat. And so when you substitute this back in, you're gonna have KC hat plus D hat, C hat, negative C hat, and then D hat. And so we're gonna get back a similar equation to M, or matrix M, or similar matrix to M, where it is a 2C plus D, C, negative C, D. So this is also close under scalar multiplication. And so now we're gonna have to check if zero's in it. And what you can do is to honestly check if zero's in it, which is like the last one and the easiest one. All we really have to do is we're just gonna we're just gonna let C and D equal to 0. So let C equal to D equal to 0. And so our M is just gonna be a matrix of 0, or the 0 matrix. So yeah, the zero element is in the matrix. So we can say that this is a subspace. So therefore it's M, which is in W, or in this case not M, W is a subset. It's a subset. And that's pretty much it. If you want to find the bases, well, I mean, you could just use the same thing as we did in the previous example. We have C and D. Where's M? Here it is. We have C and D here. And so all we have to do is just kind of like factor those out. And so our bases, which I'm gonna write here, I'm gonna write at the bottom. Our bases. Actually, let's use a different color. Nice. Okay, our bases is gonna be 2, 1, negative 1, 0, and then lastly 1, 0, 0, 1. Because if you were to multiply this by C and then by D, and then you kind of like added those together, you'll have 2C minus C, C0 plus D 0, 0, D, and that'll just be 2C plus D, C, negative C, and D. So this is our bases if they were to ask you to find it, and now we just showed that this is a subset, or our W is a subset of all matrices, all 2x2 matrices that commute with A, and it's a subset of all 2x2 matrices. So in other words, we have our 2x2 matrices, and then we have our W, So this is our vector space, and then this is our subspace. And we just show that the W is a subspace of this vector space of all 2x2 matrix. And so, yeah, that's pretty much it. Like I said, this did take quite a long time. I'm already at 20 minutes. I'm gonna try to my best to cut it down, but I won't guarantee you I will cut it down tremendously. But this was one of the long examples that I have here. I may have one more long one, but it's not going to be this long. But yeah, I'll see you guys in the next video, which is our next example.